So let's go ahead and start at the beginning. So this first question says, Co-21A, today is the 27th. Yeah. So the first question is, compute the derivatives of the following functions. Do not simplify. With an exclamation point. Please be careful. You receive little or no credit if you make a differentiation mistake. Interesting, even small one. So our first one here for 1A, and this is Grosvenor's practice exam, is we've got y equal to the natural log of x plus the square root of x. Now he does make one simplification before he differentiates, which is totally fine. And I would encourage you to do so as well. So he rewrites this as y equal to the natural log of x plus x to the 1/2. And now we're going to take the derivative, which you could either write as y prime or dy dx. I've got the function that's the natural log of some stuff. So my derivative is 1 over the stuff times the derivative of the inside stuff. The derivative of x is 1. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. And if I leave it like this, it'll be wrong, because I'm missing a very important set of parentheses. I have to have parentheses around the entire derivative of the stuff, so that it's this times all of that, not just this times 1. So make sure whenever you're taking the derivative of some stuff, if there's more than one thing being added or subtracted together, you should just put parentheses around it regardless. Even if it's just one thing, throw some parentheses around it, and you'll be safe. And then the problem said, don't simplify, so don't simplify.
What do you mean on top of the x plus x?
That'd also be fine. That would be correct as well. All right, let's look at the next one. Y equal to the arctangent of x times e to the 3x. So I see a couple things. I see an arctangent of some stuff. And then when I take the derivative of that stuff, I'm going to have to use the product rule, because I have x times e to the 3x. But from the beginning, my outer function is arctangent. We know the derivative of arctangent of x is 1 over 1 plus x squared. I might even write that on the side here. If f of x is the arctangent of x, I know that the derivative is 1 over 1 plus x squared. So then, if I want to find the derivative of arctangent of some stuff, it's 1 over 1 plus your stuff squared times the derivative of your stuff. And let's say we didn't feel comfortable taking the derivative of x e to the 3x right away. We could go ahead and write it as x e to the 3x prime. And then you could write another step, and we're not simplifying, we're still just taking the derivative. We could write another step finishing that off. So you have 1 over 1 plus x e to the 3x squared times, now we're going to use the product rule. The derivative of x is 1. We'll leave e to the 3x alone. Plus, then we switch it. You leave the x alone. The derivative of e to the 3x also requires a chain rule. So not also, I guess we do a chain from the beginning. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the 3x is e to the 3x times 3. And yes, you could write that in the numerator if you wanted to. I personally wouldn't, just because I usually like to think of the derivative of the stuff coming at the end of the derivative, but perfectly fine to write it on top as well. Cool. We'll do, yeah, I've got some ideas for other ones here. Okay, sure. Okay, let's look at question 2. Again, if you have questions, stop me along the way. Feel free to ask them. You're always welcome to ask questions. For those of you on Zoom as well, throw something in the chat. All right, so let's see here. Find the equation of the tangent line to the curve x squared y plus sine of xy plus 2y squared equal to 2 at the point 0, 1. We want to find the equation of the tangent line. You may leave the equation lying in the point slope form. You don't have to write it in the slope intercept form. Although either way, I'm sure it's fine. So to find the equation of a tangent line or any line, we need a point and we need a slope. We already have the point. So all we need is the slope. And to find the slope using calculus, we're going to find the derivative. Now, we know from the way this is written, we're not just differentiating, we're using implicit differentiation because we've got all these x's and y's mixed up together. So I'm going to start differentiating both sides of this equation using implicit differentiation. So we're going to differentiate. For x squared times y, we have to use the product rule. The derivative is going to be 2x times leave y alone plus x squared times the derivative of y is the derivative of y prime. Plus, now I've got sine of some stuff. The derivative sine of x is cosine of x. The derivative sine of some stuff is cosine of the stuff. And then we have to multiply by the derivative of that stuff, which is going to require the product rule. Derivative of x is 1, leave y alone, plus leave x alone. And the derivative of y, once again, is the derivative of y, which is y prime. Or dy dx if you like writing. Y prime is easier to write than dy dx, but whichever you prefer is fine. Plus the derivative of 2 times y squared, or 2 times some stuff squared, is 4 times your stuff to the first times the derivative of your stuff. This equation has 2 sides to it. The other side, the derivative of 2, is 0. Okay, one comment here. If this question was find y prime, it would be a lot more work, in my opinion, because you'd have to do actually an extra thing we don't usually have to do, which is you would first have to distribute the cosine of xy to y and to x times y prime, then group all the y prime things on one side and all the other things on the other side. But we don't have to do that here because they didn't ask us to find y prime. They said find the derivative at this one particular point. And if that's the case, well, they didn't actually say those words. They said find the equation of the tangent line, which meant find the slope of the tangent line, which meant find the derivative at this one particular point. When that's the case, you just get to plug in that point immediately after differentiating both sides. That is the next step. So next step, plug in x equals 0 and y equals 1. So let's see, when I do this, I'm going to get 2 times 0 times 1 plus 0 squared times y prime plus cosine of 0 times y plus 0 times y prime plus 4 times 1 times y prime equal to 0. Be careful here. Not every 0 thing goes away, but most of them do. So 2 times 0, yeah, 0, 0. Not 0. Cosine of 0 is 1 times, oops, I left myself a y here accidentally. That was a mistake. 1 times y should have been 1 times 1. Sorry about that. There should have been a 1 there. Plus 4 times y prime equal to 0. So 4y prime equals -1. So y prime equals -1/4. That is our slope. So I've got a point, I've got a slope. Normally, I would default to doing the point slope form. I would write it normally as y minus 1 equal to my slope times x minus 0. And that's a totally fine way of leaving it. Although really, I mean, I say that, but really, you shouldn't leave it. You should not leave it as x minus 0. That's not really fine, in my opinion. But here, since the point you're given is the y-intercept, you also could have just jumped straight to saying y equals -1/4 x plus 1. And that would have worked just fine as well. Yeah.
Why do you not have the other, does the y prime just cancel the 1 plus 0 times y prime?
1 plus 0. So, well, what's 0 times anything? So what I really have here is 1 times 1. So that's right. The cosine of 0 is 1. And this whole piece here is also just 1. And this one I feel like is a little confusing with all the zeros because like most of the y prime things actually just disappear because they get multiplied by 0. Right? Like that y prime there that isn't there because it's 0 times y prime. That y prime there is 0 times y prime. So it's a little weird. You should remind yourself that whenever you have 0 times anything, you just get 0. But be careful, right? Cosine of 0 is 1, e to the 0 is 1. So plugging in 0 doesn't always give you 0 everywhere. I don't know that question. What if, I'm asking anyway, what if instead they said find the equation of the normal line? Has anyone said the word normal yet? Or orthogonal? Or perpendicular? Those all are really words for the same thing. If someone says normal, orthogonal, or perpendicular, you should think perpendicular. So if they said find the equation of the normal line instead, just to kind of add on something here, the normal line at that same point, the equation, instead of being y minus 1 equal to negative 1/4 times x minus 0, it'd be y minus 1 equal to positive 4 times x minus 0. Same point, but the slope is the opposite reciprocal. So instead of negative 1/4, it's positive 4/1. And then you could write it as y equal to 4x plus 1 if you wanted to. It probably won't come up, but good to know that language. Someone could definitely ask you for the equation of the perpendicular line, and it's just changing the slope and still using the same terms. Cool. Let's look at this next question. Make sure I'm doing things the right way here. Yeah. What have we got next? The length L of a rectangle is decreasing at the rate of 2 meters per second. Problem 3. So L is decreasing at 2 meters per second, while the width W is increasing at 5 meters per second. So W is increasing at 5 meters per second. This is for a rectangle, right? So we have the length and the width. And the problem says when length is 4 meters and width is 3 meters, find the rates of change, plural, of A area. B, the length of the diagonal. So that's interesting. Okay, well, we'll start with the area. So they've already kind of told us what's changing, but I still think it's worth writing down. So the things that are changing, we know that L is changing, dl dt, the rate of change of length is negative 2 meters per second because the length is decreasing. Something's getting smaller, its rate of change is negative. On the other hand, W, the rate of change of W, so dw dt is positive 5 meters per second. Great, we have our rates of change. Oh, and then we're being asked to find what dA dt is. That's what the first question is asking. So after we've identified the rates we know and the rates we want to know, then we try to find an equation relating all the non-time variables. And it's usually pretty straightforward. It's usually the geometry thing. So like here, I've got a rectangle. I want to know the area of it. It's the basic area equals length times width. It's usually a straightforwardish thing. So here, area equals length times width. And then we differentiate both sides. We differentiate. The derivative of area is dA dt because we're differentiating with respect to time. The derivative of the product, L times W, is the derivative of L, dL dt, times W left alone, plus now we switch it. We leave L alone. We multiply by the derivative of W, which is dW dt. Tip: when you're doing these related rates problems, you should be getting all the things you need to be using in your equation. So if you know what dLdt is and dWdt is, and you're trying to find dAdt, dLdt and dWdt and dAdt should show up in your equation after you've differentiated both sides. And now we plug in. So dA dt is what I'm trying to find. Everything else I should be able to plug in for. dL dt is negative 2 meters per second. W is 3 meters. L is 4 meters. And dw dt is 5 meters per second. You can write the units in here. I don't think you need to. I'll point out that we have meters per second times meters and meters times meters per second. So both of these are meters squared per second, which is some measurement of how area is changing as time advances. So you're going to get negative 6 plus 20, which is 14. And then at the end, you should add on the meters squared per second. That's how fast the area is increasing or decreasing. Right, increasing because it's a positive rate. It's funny, in his solutions here, he doesn't write units. I would write units. Questions about that before we do the second part? So I didn't so much differentiate them as I read. So typically the problem will tell you in the words what these things are. So I was really reading the problem, which says, can you see that okay? Says that the length of L of a rectangle is decreasing at the rate of 2 meters per second. So I knew that that meant that my dL dt was going to be negative 2 meters per second. And similarly, they said the width W is increasing at the rate of 5 meters per second. So I knew that the rate of change of W, dW dt, that's how we write a rate of change, was equal to 5 meters per second. And then what I did was I have my equation and then I differentiated both sides. And then after differentiating both sides, I plugged in the values I knew. I knew that dL dt was negative 2 meters per second. I knew that dW dt was 5 meters per second. They also told me that this is happening when the length is 4 meters, when the width is 3 meters. That's how I'm getting all those things plugged in. And typically in these problems, you should be able to substitute values in for everything that you know, except for the one thing you're trying to solve for. So if you know you're trying to find dA dt, you should be able to plug in for all the other things in there. Sometimes that requires a little bit of additional work. Occasionally, you won't have all these things given to you right off the bat. I think this next problem actually shows that, so we'll just do it. No, I don't think it does actually. Well, actually, the way I'm going to do it is I'm going to do it differently than he did it because I don't love the way he did it. So let's look at part B. So part B asks us to do the same thing, except now we're talking about how the length of the diagonals of a rectangle is changing. So we're going to draw the same picture. Got L, we've got W, and now we're talking about the length of the diagonal, which he has called R. I probably would have called it S. Probably wouldn't have called it D. The only reason is, for some reason, it just feels weird to write D, 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 T. Like we just don't call the length of a diagonal D. I couldn't tell you why, other than we don't. So, yeah, I'm not a fan of the way he's done this. I feel like he's made it harder than you need to. So I'm going to show you a different way, and then we can talk about how it's done in the solutions. So here's what I would do. Well, first of all, I write down what I want to know. I want to know what dr dt is. And again, we are given that dL dt is still negative 2 meters per second, and dW dt is still 5 meters per second. Just like last time, we need to find an equation relating these non-time variables. I see a right triangle, I'm thinking what theorem? Right, that's the one. Occasionally, you might have a right triangle and need to use similar triangles. That's the other kind of thing you might do with a right triangle. But usually, there's like a weird shadow problem that uses similar triangles. But usually with Pythagorean theorem, or with right triangles, it's Pythagorean theorem. So I'm going to write that. Let me ask you all, of these three things, which is the one that goes on the side by itself? The L, the W, or the R? The R, the hypotenuse, right? The biggest thing is the one by itself. L squared plus W squared equals R squared. And then I don't need to involve any square roots here. Let's just take the derivative of both sides. So we're going to differentiate. The derivative of L squared is 2 times L times dL dt. The derivative of W squared is 2 times W times dW dt. The derivative of r squared is 2 times r times dr dt, the r dt. Okay, so here's the thing I was talking about where you might have to do a little bit of extra work to find some of the things that you are supposed to be able to know. We should be able to plug in for everything except for the one thing we're trying to find, dr dt. If you really wanted to, you could also divide both sides by 2, right? Right, I've got 2's everywhere. I could get rid of them. So let's divide both sides by 2. I'll write that down. So we've got L times dl dt plus W times dw dt equal to R times dr dt. So I'm going to plug in L equal to 4 meters. dl dt is negative 2 meters per second. W is 3 meters. And dw dt is 5 meters per second. And now here's, sorry, 5. I just want the 5. I don't need the units, James. Here's where we actually have to figure out what R is, right? We don't know what R is, but we should be able to know what R is because we're just trying to find dr dt. So that's where I'm actually going to use the Pythagorean theorem here and plug in the values of L and W to find R. So L was 4, W was 3. How convenient. 4 squared plus 3 squared equals R squared. So 16 plus 9 is 25. Right, exactly. You picked, which is pretty typical. Most of the time when you have to find this other value, they've often made nice choices for your triangle sides, like 3, 4, and 5, or 5, 12, and 13. Those are pretty common choices. So then that's the value we can plug in for R right here. And now we can solve for dr dt. Negative 8 plus 15, that's going to be 7 equal to 5 times dr dt. So dr dt is going to equal 7/5. Or if you prefer, 1.4. What are my units? More time? Yeah, meters per second, because R is a measure of length and per our unit of time. So it's just whatever our length unit is per whatever our time unit is. This is the same answer that he got doing it a different way. I don't think we need to write it up, but I'll just show you there. So here's the way he did it. He decided to say that, not incorrectly, that L squared plus W squared is R squared, and then R is equal to the square root of W squared plus L squared. Or if you prefer, W squared plus L squared to the 1/2 power. And then he differentiated both sides. The derivative of R is dr dt. The derivative of some stuff to the 1/2 power is 1/2 times your stuff to the negative 1/2, or 1/2 times the square root of your stuff. And then times the derivative of the inside stuff, which is 2 times W times dw dt plus 2 times L times dl dt. This feels like more work to me. The only way you could argue that this is less work convincingly is that doing it this way, you technically don't have to find R. But really you do, because really it's right there. You're still finding it, it's just written as the square root of W squared plus L squared instead of written as R. So I think if you can avoid introducing square roots into a problem like this, you should. There's no real value to doing it this way versus this way. But you can choose whichever way you like. But yeah, to be perfectly honest, I don't think I've ever seen anyone actually do a problem like this that way. Like, it's just so atypical. Everyone I've ever known would always, like, if you asked anyone at the AATC, they would all do it this way, and they would be like, "What are you doing? It's so weird." Like, it's just not done that way because you're making it harder on yourself. So if you did it this way, it would be perfectly correct. Your answer would be perfectly right. We've got the same number. The process is right. There's nothing to worry about doing it a different way, even if it feels like it might be slightly. That's not wrong. It's totally right. Questions about that? Okay. Well, let's look at this. Problem 4. In all parts of this problem, consider the function f of x is equal to x squared plus 4 over x on the interval on the domain, which is from 1 to 4 inclusive of the endpoints. I will point out it might be worthwhile to simplify this we can write that f of x is equal to x squared over x plus 4 over x, which simplifies as x plus 4 over x, or x plus 4 times x to the negative 1. I don't actually know if that's going to be helpful, but it might be helpful. And it's not hard to do. So part A. Determine the global maximum and minimum of y equal to f of x on the domain given. So find the global max and min. Okay. The process for this is finding all critical points on the interval and the endpoints, and then evaluating them evaluating the function at those points. So the first step here is to find the critical points. Okay, so you could I feel like the way I've done this looks easier to me. I don't know, we'll do it both ways. So taking the derivative using the quotient rule, I'm gonna get the bottom times the derivative of the top. I should really write f prime here, sorry. F prime of x is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that's going to be equal to 2x squared minus x squared minus 4 over x squared, which is just x squared minus 4 over x squared, which is x minus 2 times x plus 2 over x squared. And we set that equal to either being 0 or undefined. There are technically, we'll have to talk about this more later, but for now, I would say there are technically 3 critical points, even though that's not really right. I'll talk about why in a second. So my critical points are going to be x equal to 2, x equal to negative 2, and technically 0. Here's the story about 0 in this case. 0 is not a critical point because 0 is not in the domain of the original function. Right? If you look at the original function, definitely undefined at 0. Which means we're probably, what kind of feature, if we graph this thing, what kind of feature would we have at x equal to 0? Not a V, but it starts with a V. A vertical asymptote. And so what that means is the function is not defined there, can't have anything, can't have a maximum or anything. But what is also important about those points is that the sign of the derivative can change from one side of the vertical asymptote to the other side of the vertical asymptote. So even though it's not a true critical point, we always include it on our number line when we're talking about finding relative maxima and relative minima. I usually call it a pseudo critical point because it's not really a critical point, but it's important enough that we need to include it. In this problem, it's not even an issue because 1, 0 is not in the interval we're looking at. So we don't even care. 0, goodbye. What else should I say goodbye to? Yeah, negative 2 is also not in the interval. Most teachers, when they ask you to find the global extrema on an interval, will almost always make it so at least one of those points that's a critical point is not in the interval. So that you have to actually be thinking, oh yeah, we're only using the points in the interval. I have to exclude any that aren't. So then we take all of our critical points that are in the interval and the endpoints and plug them into the original function. So we're going to look at f of 2, f of 1, and f of 4. F of 2 is 2 squared plus 4 over 2, which is 4 plus 4, 8 over 2, which is 4. F of 1 is 1 squared plus 4 over 1, which is 5. And f of 4 is 4 squared plus 4 over 4, which is 16 plus 4 over 4, which is 20 over 4, which is also 5. How annoying is that? It's annoying because everything is something. Usually one of your points is it. So you technically have, yeah. So, and this is where you need to be careful about how the question's asked. This question specifically says, determine the global maximum and minimum. So I would say all the things. So I would say we have a global minimum at 2, 4. That's probably the easiest way of writing it. You could also say there's a global minimum at x equals 2 with a value of y equals 4. X is the where, y is the value. The minimum occurs at x equals 2 with a value of y equals 4. We have global maxima, plural, at both 1, 5 and 4, 5. Or you could also say we have a global maximum value, maximum of 5 at both x equals 1 and x equals 4. And then he also asks, what's the range of this function on this domain? Well, that's easy enough. No, yeah, that's easy enough because this theorem is only applicable. So the theorem that we just used that we didn't actually talk about is called the extreme value theorem. It says that a function that is continuous, which this is, on a closed interval attains an absolute max and an absolute min. This function, x squared plus 4 over x, is not continuous everywhere. Where is it discontinuous? For sure. 0, right? It's undefined to 0. It's for sure discontinuous there, but it's definitely continuous on the interval that we've been given. This function is for sure continuous on the interval from 1 to 4. So the maximum value and the minimum value also give you the upper and lower limits of your range. So here, the range of this function, the range of f on the interval from 1 to 4 is going to be a low value of 4 and a high value of 5. So if you're asked an extreme value question and asked to find the range is literally just the minimum value to the maximum value. And you're guaranteed to get everything in between because of the intermediate value theorem. The function is continuous, and so you have to get all the values. So you don't have to be like, we get 4 or 5, and maybe, no, not maybe the stuff in between, definitely the stuff in between because of continuity. Cool, that's not a terrible question. Just to point things out, if we'd done this alternatively, like if we had found f prime of x equal to 1 minus 4x to the negative 2, I don't know if that's better. You might think it's better, you might not. Set that equal to 0. You can write this as 1 minus 4 over x squared equals 0. Or multiply everything by x squared, and you get x squared minus 4 equal to 0. X equal to plus or minus 2. And then you also have to worry about x being 0. It might be better, it might not be better. It's kind of depends on what you feel about that. So do it whichever way seems best to you. All right, let's look at the next one. Part B. This is interesting. I feel like I've not really ever seen range questions like this. Which is fine, they're just different. Let g of x equal sine of pi times f of x. Well, there was another question like this that somebody asked me to address, which I'll look at in a second here. Assuming, yeah, I did. I hope I wrote it down somewhere. I thought I did. I always write things down in my office and then forget to bring the piece of paper sitting on my desk that has the things written down. Okay, well, fine. We'll see if I can find it. So sorry, I got distracted there. Let g of x equals this, determine the range of g of x on the same domain, which goes from 1 to 4. Okay. So basically, you can say that g of x equal to sine of pi to the f of x. We know that f of x is going to be between 4 and 5, because that's what we just found, right? The range of f of x was between 4 and 5. So then g of x, yeah, I don't love this. I'm trying to think about how I would do this. I mean, I guess you're going to be bounded by sine of 4 pi and sine of 5 pi. And you're going to need all the values in between. Sine of 4 pi is 0. Sine of 5 pi is 0. I don't know about this, young. Let's read what he wrote here. Same as the range of okay, you're going from 4. Oh, sure. Yeah, okay. I see. Yeah, that's that. So okay, let's think about it this way. Yeah, that's not helpful. So if you think about the unit circle, right, you're going 0, pi, 2 pi, 3 pi, 4 pi. So right here at 4 pi, sine 4 pi is 0. And then when you go from 4 pi to 5 pi, well, sine goes from 0 to 1 to 0. So it looks like our range here should be 0 inclusive to 1 inclusive. And sine goes from the beginning of quadrant 1 to the end of quadrant 2. You get all the values sine would hit, which are all the values from 0 to 1. If on the other hand, we had been going, say, from 5 pi to 6 pi, then our range would have been -1 to 0, because we would have had the bottom half of the unit circle, even though it's an interval of the same length. It's the other half, kind of. That's a funky question. I don't know if I like it that much.
It's in the rotation. I don't get it, like too much that they like rotate, like circles and circles.
Well, let me ask you a different. Let's say let me ask a slightly different question, which I think is actually pretty good. Let's say we had h of x equal to cosine of pi times f of x on the same interval. I want you all to write down what you think your range is going to be if we're going from here to here. Go ahead, write down your answer while I put my pens. I'm gonna look for that other question I thought I wrote down somewhere. It's probably sitting on my desk. I know what I can do. I can look for it. Someone give me 1 second. I'll find it. I'll see if I can find that. So, cosine, if we look from 4 pi to 5 pi, we're getting all of quadrant 1 and quadrant 2, and cosine goes all the way from +1 to -1 on those angle values. So here, the range for h of x would be -1 to 1 if it was cosine of pi times 5x. Cosine of pi times f of x, sorry. Yeah.
Where did you get 4 pi and 5 pi from?
Sure. So the original question was sine of pi times f of x, where again, the range of f of x was between 4 and 5.
Oh,
So then we're just taking f of x with going from 4 to 5. So pi times f of x going from 4 pi to 5 pi. Other questions about this?
Can you explain again why the range is 0?
Sure. So really, so kind of what we're looking at, another way to think about this is if you actually, like, if you graph the sine function, right? It's the usual kind of deal. I'm gonna try and draw like 3. And so from 0 to 2 pi, it does this. And then from 2 pi to 4 pi, it does the same thing. And then from 4 pi to 6 pi, it does the same thing. Wow, my graph is getting worse and worse every time. But from 4 pi to 5 pi, right? So if the inputs go from 4 pi to 5 pi, the outputs are up here, which are between 0 and 1. That's maybe another way of seeing it that might be easier for some people. To me, this feels less nice. I definitely see this much more easily. I'm like, oh yeah, I'm going from 4 pi to 5 pi in the unit circle. So the sine values, which are the y values, right? My y value here is 0. My y value here is 1. My y value here is 0. I never get any negative y values here. On the other hand, my cosine values are 1, 0, -1. So I go all the way from -1 to 1 for the cosine range. I could honestly see him asking this exact same question, but changing it to cosine or something very similar. Like I think it'd be a good slight alteration on the question that like it's still similar enough to the practice exam, but you feel like it's like not that different, but it's making you think a little bit outside the box. So I would do that. I mean, that's a good modification. Oh yeah, sorry, question.
So, what do you, can you like, explain like, so we say g of x equals sine of, 5 times f of x, like what is f of x?
F of x, so f of x was the function from before. So this is equal to, you could actually write it out, right? Sine of pi times, what is it, x, x squared plus 4 over x. And that's, I mean, yeah, but I don't think that really helps us see it. All right. I'm not sure, there's a chat comment that says, I prefer your way more, great. I don't remember in reference to what, but I'm happy to hear it regardless. Trying to find this question that someone else had for me. So let me minimize this for a second. Sorry, there are things that are hidden from, oh my gosh, there's too many things on my screen. Sorry. I know, but it's bothering me. Oh my God. Okay. Assignments. Sorry, so if the person who asked, so someone asked a question like where the range, it was like the range of something like x cubed plus some lower things was something, and then they asked like, then you had to square the function and ask what the range of that was. But I will find it here. Sorry, I did this twice today where I looked, I thought I wrote a thing and thought I took it with me and then didn't take it with me. Let's look at the, I know, but it's okay. But now if I can actually find it, because there's like a bunch of these to look at. This one. You should think about if you have other questions like to ask. While I try to find this question. Who was it from? Oh, maybe someone in the chat wrote down. Thank you, appreciate it. Good, it's gonna take me forever to get there too, because that's like one of the last names in the list. Cool. There we go. Awesome. Okay, here's the question that was asked. So the question was, Grosvenor did an example where the function was f of x equal to 2x cubed minus 3x squared minus 36x plus 14. And we had to find first the global max and min on the interval from, I think, 1 to 4, also 0 to 4. So we'll do that first, and then we'll ask the second part. Okay, cool. So this is a good practice. Global max min, so we're going to find our critical points. To take the derivative, we've got 6x squared minus 6x minus 36 equal to 0. If someone doesn't hate you all, they'll probably try to make something that factors nicely. You can either factor out to 6 or divide both sides by 6, since there's a 0 on the other side. So 6 times x squared minus x minus 6. This does factor as x minus 3 times x plus 2. So when you do this, you don't need to set the 6 equal. I've seen a lot of people like in drop-in or offstars, like they set each factor equal to 0. There's no value from setting 6 equal to 0, right? 6 equal to 0, not true. There's no x to solve for there. Setting this equal to 0 gives you x equal to 3. Setting this equal to 0 gives you x equal to -2. And as predicted, he's given you something where one of your critical points is not in the interval we're looking at. That is something you should be on the lookout for if you have to find some global maxes and global mins. I would be willing to bet that at least one of those points you find is not going to be in the interval you're supposed to be checking. So then take all these and plug them into the original function. So we're going to look at f of 0, f of 3, and f of 4. And it's not going to be pretty here, but we'll do it anyway. F of 0 is not bad. It's 0 minus 0 minus 0 plus 14. F of 3 is going to be a little bit of work. It's going to be 2 times 3 cubed, which is 2 times 27, minus 3 times 3 squared, minus 36 times 3 plus 14. 2 times 27 is 54, minus 3 times 9 is 27, minus 36 times 3 is 90 plus 18, which is 108, plus 14. So then you've got 27 plus, I don't know, it's a number. There's so much math to do. Let's see. 27 minus 108 is going to be negative 81, plus 14 is going to be negative 67. And then finally, f of 4 is going to be also gross. 2 times 4 cubed is 2 times 64, minus 3 times 4 squared is 16, minus 36 times 4 plus 14. So you've got 128 minus 48 minus 36 times 2 is 72. 72 times 2 is 144 plus 14. Here's what I would notice. 128 minus 48 is 80. Negative 144 plus 14 is negative 130. And 80 minus 130 is negative 50. So the absolute max is 14. And it occurs at x equal to 0. The absolute minimum is negative 67. And it occurs at x equal to 3.
What do you don't find like F of 2 because of
F of negative 2? Where is 2 ever in the story?
the interval between 0 and 4?
Well, let me ask you, why am I not finding f of 1?
Yeah, that's
So we are only concerned with the endpoints and the critical points. Because, so what's happening here basically is you've got something that looks like this, and I'm going to draw it not perfectly here, but maybe it's doing something like this. So here's 0, here's 4, and here's your critical point at 3. These are, right, 1 or 2 can't give you an absolute maximum or an absolute minimum because the derivative there is either positive or negative. The function's increasing there, it can't be a maximum because it's going to be bigger to the right. It can't be a minimum because it's going to be smaller to the left. Similarly, if the function is decreasing there, it can't be a maximum because it's bigger to the left. It can't be a minimum because it's smaller to the right. So to be a possible max or min, has to be a place where the derivative is either 0 or undefined.
okay. So we just only take the areas like
We're only taking the critical points, which we're getting by setting the derivative equal to 0 and then solving.
How do you get, are we setting it equal to 0 or how?
I'm plugging in all my critical points. Oh, sorry, I'm setting what equal to 0.
On the left side where it's like f not of x, it's 6x.
Right, I'm setting f prime of x equal to 0.
Oh, we're setting it equal to 0.
Yep.
Oh,
That's how we find critical points. Technically, I should have said equal to 0 or where it's undefined, but we knew that since this was a polynomial, it's defined everywhere, and we're not going to think about the undefined part because it's not applicable.
I just found like I asked that question because like when we had the notes,
Mhm.
I was wondering that like that's the endpoint, right? And then I was wondering that like why we're not getting 2, like probably 2 gonna be like
Because we just don't have as many. Like, so
for like in this particular question, like in the question that we're gonna have, like we might get like we only get this like area like from A to like my hand. Is that what it's gonna be?
maybe, I don't actually know what the picture looks like here, but
Yeah,
let me address that after class.
sure.
So now the second part of this question, which is the part I thought was strange-ish, is now we're asking what's the range of g of x equal to f of x squared? So first of all, the range of f of x is going to be from negative 67 to as high as 14. Now, this is a good question. This is a tricky-ish question, I feel like. So now the range of g of x, which is equal to f of x squared. So what's the lowest value g of x could get? That's the lowest value f of x can get. But g of x is equal to f of x quantity squared. I can go lower. I can go lower. You should be able to get as low as 0. Because certainly, does f of x have to equal 0 somewhere? Yeah, because you get all the values between -67 and +14. So certainly there's some value where f of x is equal to 0. So g of x certainly should be able to be going as low as 0. Could g of x go any lower? If it's equal to some quantity squared? Definitely not. G of x has to be greater than or equal to 0. So that's the lowest value. Okay, how high can we go? I can go higher. Not that high. Thank you. I'm gonna say -67 squared, but same answer, right? Whatever, right? So you can get as big as the biggest thing squared, and the biggest thing squared here is -67 quantity squared, which ends up being the same as 67 quantity squared. Right, so we had to take this is a thoughtful question. We had to take the number that was larger in absolute value and square that to find the upper end of the range. It's tricky, for sure. Sorry. There we go. Cool. All right, I think there's still one more question on this practice exam. One more question, 2 more parts. Yeah, the mean value theorem. No, not the mean value theorem, but I definitely wanted, yeah, that's what we'll spend the last amount of time probably talking about the mean value thing here. Don't loss. All right, so the last question here, question 5, says let f of t equal 3t minus sine of 2t. The position S, interesting, so position S at time t greater than or equal to 0 of a particle moving along the coordinate line. So like the x-axis is what I'm thinking of. Is given by S equal to f of t, which feels like a lot of writing for not saying a whole lot. You could just say the position is given by f of t. Find the smallest time, so part A, find the smallest time that is greater than or equal to 0 where the acceleration is 4. For what? Nobody knows because there aren't any units anywhere. So if nobody gives you units to start with, don't sweat it. All right, so for the acceleration to be equal to 4, that means we're going to have to take the second derivative and set it equal to 4. So the first derivative here is going to be 3 minus cosine of my stuff times the derivative of my stuff. And then the second derivative is going to be 0 minus the derivative of cosine of some stuff is negative sine of that stuff times the derivative of that stuff. And then we also have another 2 already out there. F prime of FL prime of t, sorry, not 0. So my second derivative is equal to 4 times sine of 2t. And I want that to be equal to 4. Because that's what the problem said. Find the smallest time t where acceleration is 4.
That's when it's the third derivative or-
Second derivative. Acceleration is the second derivative of position. Velocity is the first derivative of position. Question.
Where like the two ahead of cosine get off the first derivative? It seems like you included the second.
Well, so basically I'm thinking. So I have cosine of my stuff times the derivative of my stuff. And then here, so everything in here, all of this in the parentheses, all that's the derivative of cosine of 2t. And then that 2 just hung out. Or essentially, every time you take the derivative of sine of 2t or cosine of 2t or some trig function, sine or cosine of some multiple of t, every time you differentiate that, you're going to multiply by another factor of that constant. So I know that if I took the next derivative, if I find f triple prime of t, it would be 8 times cosine of 2t. And the next derivative would be 16 times whatever of 2t. And then 32 times the prime. Every time you differentiate, you're going to multiply by another 2.
Do you write the ending as like 2 plus 0, or does the final like 2? So you don't prove it. Like if like the ending point is it's like 2x, then you do it.
When you say the ending point, I'm not sure what you mean exactly.
Like, do you only do the sign?
Okay, yes. So there's two ways you can think about it. The way I'm usually thinking about it. So if I have like, if my function is just like sine of 3t, then the derivative is cosine of 3t times 3. Right? Cosine of my stuff times the derivative of my stuff, which I would prefer to think of as 3 times cosine of 3t. You can, so here's what you, right, order of multiplication doesn't matter, and we like writing constants first. And now to take the next derivative, you can think of it in one of two ways. The way I'm thinking of it is I have a constant multiple, and that constant multiple just hangs out. And the derivative of cosine of some stuff is negative sine of the stuff times the derivative of the inside, which is 3. So I'm getting negative 9 sine of 3t. Or you can think of this as a product rule. The derivative of 3 is 0 times, doesn't matter, but all right, cosine of 3t, plus the 3 hangs out, and now the derivative of cosine of 3t is negative sine of 3t times 3. Either way, you're still getting negative 9 times sine of 3t. I would always prefer to think of it as just a constant hanging out, but if the product rule makes more sense for you, that's also totally straightforward and fine. Is that what you were asking? Okay, that's what so I thought you were asking, but it was to clarify.
We were multiplied by 2 because of the chain rule, right?
Correct.
Oh,
So from this derivative to this derivative, I multiply by 2 because of the chain rule. From this derivative to this derivative, I'm multiplying by this 2 because of the chain rule. And this 2 is just sticking around because it's a constant multiple. So now solving this equal to 4 is the same as saying I want sine of 2t to equal 1. What's the smallest angle on the unit circle where sine is equal to positive 1? Pi over 2. So I'm going to set 2t equal to pi over 2, and then multiply both sides by 1/2. So t equals 1/2 times pi over 2, which is pi over 4. And that's our answer. There would be other angles as well, right? 5 pi over 2, 7 pi, or 9 pi over 2, 7, but he wanted the smallest one. The pi over 2 and then divided by 2. Excuse me. Okay. The second part of this question is how many times is the particle positioned at s equal to 1? Interesting. I'm really curious about his solution here. So the question is, at how many times is the particle positioned at s equal to 1? So ignoring his solutions for a second, I would think of this as trying to solve. Maybe we're not actually trying to solve though, because they didn't ask to find the times. They said how many times. So we're saying not solve, but how many solutions would there be to 3t minus sine of 2t equal to 1? That feels like a challenging question. Like, really? Well, think about the graph. So if I was going to try and graph 3t minus sine of 2t. Here's what I know. Three t looks something like this. And sine of 2t looks something like this. So if I subtract those from each other, I'm going to be above 1 most of the time. Right? I'm going to do some sort of like weird kind of oscillating thing. But essentially, I'm going to do something like, I don't know, maybe like this. Kind of like that. So eventually, I'm always going to be above the line y equals 1. But the question is, like, how many times am I going to equal 1? And I don't, like, looking at this question, I really don't have a good intuition as to what you're supposed to do. Like, I don't know. Really don't know. Like, really, really, really don't know. So I guess I'll look at the solutions and see what he's doing here. So he's observing that the derivative is bigger than 1. I see. Okay. Okay. So this is an application of Rolle's theorem. That's smart. So here's what he's saying. He's looking at the derivative. Saying, okay, well, my derivative is equal to 3 minus cosine of 2t times 2. Whereas I would write it 3 minus 2 times cosine 2t. And he's noting that this derivative is always bigger than or equal to 1. Right? Cosine, the biggest this part can ever be is 2. So the smallest this can ever be is 3 minus 2, which is 1. So this is bigger than or equal to 1 for all values of t. Or in other words, the derivative is always positive. Or in other words, the function's always increasing. Doesn't feel like Rolle's theorem is really what I want to say here. Yeah, it's interesting. Yeah, sorry, I'm sorry. I'm like, yeah, okay. So I don't love the use of Rolle's theorem personally. I would say f of t is always increasing because f prime of t is greater than 0 for all t. So if a function's increasing always, it can only hit the some y value one time, right? Because you can't turn around and hit it again. So if we're trying to see how many times this is equal to y equal to 1, right? We can be increasing, but then we can't turn around and hit it again. We have to just keep increasing like that. So there's at most one solution. But is there one? Well, that's where the intermediate value theorem comes into play. So we would say, well, we can see that f of 0 is 3 times 0 minus sine of 2 times 0, which is 0 minus 0, which is 0. And then pick some obscenely large value, like f of 2 pi. That's not even that large. That's going to be 3 times 2 pi minus sine of 2 times 2 pi. That's going to be 6 pi minus sine of 4 pi is 0. That number is certainly less than 1. That number is certainly bigger than 1. So between 0 and 2 pi, the function has to attain a value of 1. So exactly one solution. Yeah. I don't love the phrasing of this question. I feel like it's not phrased in a way to me that is obvious to have had to use the intermediate value theorem. Yeah, if he'd said how many times does how many solutions do we have to this function equal to 1? I feel like that would have made it a little bit easier to see that we might need to use the intermediate value theorem. But yeah, that last question's a little tough, I'm not gonna lie. Questions about that question? I suppose I should write more words here. Right, so my function, right, was 3t minus sine of 2t. Right, and I'm taking the derivative, which we've already done before, and I'm observing that the derivative is always positive, meaning that the function is monotonic. It's always increasing or always decreasing. In this case specifically, always increasing. And if something's always increasing, it can only ever be equal to one value once. If there are not multiple solutions to this function equal to anything, there's only one solution. And then we showed that there was actually a solution by showing that the intermediate value. So then we can say by the intermediate value theorem, there is some value t between 0 and 2 pi where 3t minus sine of 2t does in fact equal 1. That's what we're saying with all this.
Is the 1 different when we use greater than or equal to 1, or is it like happenstance? Like, can I just like say derivative greater than or equal to 1, or is that like 1 top?
This one here,
Yeah.
this one is specifically because we know that cosine of 2t is always between -1 and 1. So the biggest this could be is 1, meaning the biggest this could be is 2. So the most we're subtracting from 3 is 2. I can't subtract 2.5 or 2.9 or 3 because this never grows any larger than 2. And the biggest 3 minus this could ever be, sorry, the smallest 3 minus this could ever be is 1. It'll never be smaller than 1. But it's really based on the fact that we have a trig function here, cosine. That cosine is what's giving us this inequality. Yeah.
Oh, where do you get between 0 and 2?
2 pi?
Oh, 2 pi?
Yeah. Because I picked 0 and 2 pi. He picked different numbers, right? He picked 0 and pi over 2 in his solutions. But I was going for an answer that was easier just to be like, oh yeah, I know 2 pi is for sure going to be big enough to be over 1.
So basically, since we're looking like to see where it's what is the word it's x equals 1.
Mm-hmm.
So we have to take look at a point smaller than 1 and bigger than 1.
Not a point smaller than 1, bigger than 1. A point where the output is smaller than 1 and the output is bigger than 1.
Oh,
Yeah, it's a little tricky. Okay, we have 6 or 7 minutes here. Let's briefly talk about the mean value theorem. The mean value theorem. which is abbreviated as the mean value theorem. We'll actually start with Rolle's theorem, because Rolle's theorem is just like a special case of the mean value theorem. So Rolle's theorem says the following. If f of x is continuous on some closed interval, differentiable on the same open interval, and for Rolle's theorem, f of a is equal to f of b, then there must be some number, we usually call it c, in the open interval from a to b, such that f prime of c is equal to, so I'm going to phrase it in the way that's similar to the mean value theorem. It's just that f prime of c is equal to f of b minus f of a all over b minus a. It's just in this case, what's f of b minus f of a going to equal? If I said that f of a had to equal f of b. If these two things are equal and I subtract them, you get 0. This theorem is not lovely to read, but it's really nice if you draw a picture. Here's some of the pictures. There's A, there's B, there's f of A, and f of B being the same. And maybe my function looks like this. Oh yeah, there has to be a point in between A and B where the derivative is equal to 0. Or maybe it looks like this. Or maybe it does a bunch of stuff, right? Maybe it's like that. And you have multiple points where there's a 0 derivative. All the theorem says is that if the endpoints have the same y value, the function is continuous and differentiable, there has to be a point in the in the open interval where the derivative is equal to 0. You might ask yourself, why couldn't I have a picture like this? Does it look like on the picture I drew, is there a place where the derivative is 0? Where I have a horizontal tangent line? Definitely not. Does this function that I've drawn meet all of the criteria of the Rolle's theorem? Is it continuous from A to B? Is it differentiable from A to B? Definitely not. There's a pointy point. This is not differentiable on the open interval. Specifically right there. You've got a sharp point, you've got a cusp or a corner, fails. So does not meet the criteria. The mean value theorem is the same as Rolle's theorem, except we're just going to leave off the part where f of a and f of b have to be equal to each other. So the mean value theorem is pretty much, I mean, it is just a generalization of Rolle's theorem. So the mean value theorem says the following. Mean value theorem says if f of x is continuous on the closed interval from A to B, differentiable on the open interval. And again, it can be continuous and differentiable on larger intervals as well. This is just the bare minimum. Has to be continuous at least on the closed interval from A to B and differentiable at least on the open interval from A to B. But usually their functions, they're continuous differentiable like everywhere. Then there must be a number C between A and B, or in the open interval from A to B, such that f prime of C is equal to f of B minus f of A over B minus A. And the only difference here is that in this case, we're not saying the endpoints have to have the same function value, so this doesn't end up equaling 0. The geometric interpretation here is that for any continuous differentiable function on an interval, there has to be some point in the interval where the slope of the tangent line is equal to the slope of the secant line connecting the endpoints. Or in other words, graphically, oh my gosh, maybe. If your function does something like this, well, if you look at the slope, I have a ruler. Time. So, right, the secant line connecting the endpoints of that interval, there must be at least one point between A and B where the slope of the tangent line is equal to the slope of the secant line, or the tangent line is parallel to the secant line. And it looks like it can be right about there. That's the whole idea with the mean value theorem. Or in other words, there's a place where the instantaneous rate of change has to equal the average rate of change. So here's a fun question. I know we only have a minute, but I'm asking anyway. So, speed limit back in the day is 55 miles per hour. Car drives over a 1 mile bridge. In exactly 1 minute. Did they break the speed limit? So if you drove 1 mile in 1 minute, how fast were you driving?
60 miles per hour?
Right. Were you driving 60 the whole time? Maybe. I don't know. But I know for sure that the car's average speed was 60 miles per hour. Does that mean that they were going over 55? For sure. Because even though they might have been going under 55 some of the time, the mean value theorem tells us that if your average speed was 60, your actual speed, at least at one moment, had to have been 60. Assuming you were driving in a continuous differentiable way, right? You're not slamming on the brakes or slamming on the gas. You're accelerating and decelerating smoothly so that it's differentiable. Okay, fine. So yes, you would have broken the speed limit because your average speed was 60, so your instantaneous speed had to be 60. Maybe you're driving 50, like the first 30 seconds, and 70 to the last 30 seconds, and from that minute you went from 50 to 70 real quick, you still hit 60 miles an hour. So that's really what you should think about when you think about the mean value theorem. That your instantaneous speed has to, at some point, equal your average speed. We'll talk more about it on Thursday.